Hello everyone, welcome to the next lecture of MOSFETs. Today we are going to talk about more details related to the conductance of the channel. We're also going to cover, more importantly, the IV characteristics. We will also see that in the last lecture we operated the MOSFET with a small VDS. Today we're going to talk about what happens when the VDS value is increased, and we will also cover the topics on what are the different regions or different modes of operation of the MOSFET transistors. We will see that how it can be operated into different regions, kind of a cutoff region, a triode region, a saturation region. Okay, so we're going to cover all of that. So this is where we were in the last lecture. We ended up developing this equation. This equation is the drain current that flows from the drain to the source terminal as we apply a small VDS, a drain to source voltage. That VDS value is relatively very small as compared to the overdrive voltage. And if you remember, this overdrive voltage is this extra or extra voltage more than the threshold voltage that is applied at the gate terminal, right? So overdrive voltage was gate to source minus threshold voltage. So this is essentially the effective voltage that is helping to induce the channel and collection of all the charges and helping with the conductance. We also derive this conductance of the channel relationship. It depends on three factors. It depends on mu and Cox, W over L, and V over V. So let's start our lecture today with talking more about these three factors very quickly, and then we will move to the IV characteristics. Okay, so the conductance of the channel depends on three factors. The first one is mu and Cox. Mu and Cox is called as a process transconductance parameter. This process word is essentially the fabrication process and all the details and related to the technology that are used to fabricate these transistors. Right, so it is determined by the fabrication process technology. This process parameter depends on two factors. One is this mobility of the electrons, and the other one is the capacitance of the oxide. Again, this mu n is the mobility of the majority charge carriers of that are being collected in the channel in the particular MOS transistor. For an NMOS, these are electrons. It will be mu n. For a PMOS, it will be mu p. So when we discuss the PMOS transistor, these specific things related to the PMOS will become more clear. And the second one is the Cox, which is the oxide capacitance of the oxide. This process transconductance parameter is also written as K n dash, right? So it is also written as K n dash mu n Cox. You're going to see this term appearing K dash n or K n dash very often in the coming lectures and the exams and the homework problems. So just remember what is this K n dash, mu n Cox, right? And it is a product of the mobility and the capacitance. And over here, the subscript n denotes the n channel or the NMOS, right? For a PMOS, it will be K dash P, or for a PMOS, it will be K dash P. Okay. Right, so these are the dimensions. You can easily find out these dimensions. This is our real equation of the electron velocity that we calculated. So this equation may help while you are evaluating all of these dimensions or the units of these, more importantly, the units of these mobility, the capacitance, and the K n dash. Okay, so let's look at the second parameter over here for the conductance. That second parameter is this W over L ratio. And this W over L is essentially what is called as the aspect ratio. It is the width of the channel to the length of the channel, right? And as this aspect ratio is increased, going back to the equation again, as this aspect ratio is increased, the conductance value, directly proportional, so the conductance value will increase. So let me write this down. So our GDS is directly proportional to W over L. So as width of the channel is increased, the conductance will increase, and as the length will decrease, the conductance will increase, right? And now the length of the channel was, if you guys remember, the length of the channel was the separation in between the source and the drain ends, right? Here is the figure of the device structure. So this was the length of the channel, and this was the width of the channel. So this was the width and this was the length. So as you reduce the spacing in between, or the separation of the source to the drain, as you decrease this length, the conductance will increase. And as you increase this width, it will accumulate more and more charges, so the conductance will also increase. Okay, so let me go back to, okay. So the channel conductance is directly proportional to the width and inversely proportional to the length. And when people are designing transistors for specific applications, whether they are for amplifiers or microprocessors, they want to operate the transistor in certain regions. What does this operating the transistor in certain regions mean? This will become more clear in the next lecture. However, we have to operate the transistor on specific regions of this IV characteristics. So essentially, for specific applications of the transistors, this W over L ratio is designed in specific ways. Another important consideration over here is the minimum, something that is called as L-min. L-min is the minimum length of the channel that is possible for the fabrication processes that are currently being used in the industry. And over the years, with the more advancements of the technology, of the fabrication technology, this possible value of this L minimum is constantly being decreasing, right? So we know that the smaller the value of the L, greater will be the conductance, right? So we want to reduce the value of the L. So one is to increase the conductance, is also to pack more and more transistor in the same area. So L minimum is important and depends on the fabrication process. Over the years, it's been improving. So in 2014, for example, for the MOS technology that was commercially available, the smallest L-min was 32 nanometers, and it's been decreasing over the years. Okay, another important thing over here is that as you will decrease, in order to keep the capacitance between the gate and the channel the same, if you will vary the L minimum, the oxide, the thickness of the oxide needs to be varied as well. Over here, for example, right, if you will reduce this length of the channel, the thickness over here, I can replace this value by, for example, the thickness needs to be reduced as well to increase the oxide capacitance and to maintain the same capacitance between the gate and the channel. So that is why when if you are decreasing the L minimum or the L length of the channel, the oxide thickness also needs to be reduced to maintain the same capacitance. When the thickness of the oxide will be reduced, the oxide capacitance per unit area of the channel will increase, right? So to maintain the same capacitance. Okay. So this another kind of a parameter now we're going to define is called as a MOSFET transconductance parameter. The first one that we defined, this Kn dash, was mu n C ox earlier. So this was the process transconductance parameter, right? Please remember the difference. One is a process transconductance parameter, other one is a MOSFET transconductance parameter. So the process transconductance parameter was the first term, mobility and the oxide capacitance. And the MOSFET transconductance parameter is the product of this transconductance process parameter multiplied by the aspect ratio, right? So Kn is essentially K dash n multiplied by W over L, or mu and C ox into W over L. This is just another way to simplify writing the equations. However, please do remember again the difference or the distinction in between these two terminologies, because these specific notations will appear again and again in the exam problems, in the homeworks, in the later part of the slides and the lectures. So have this distinction in mind very clearly, that the process conductance parameter is the mobility and the capacitance of the oxide, and the MOSFET transconductance is the product of the process transconductance multiplied by the aspect ratio, width and the length of the channel. Okay, this is what I just wrote. Okay, now the third factor again in the conductance value over here is the overdrive voltage or overdrive voltage. Okay, we saw that this overdrive voltage again is this extra voltage beyond the threshold voltage that is needed. So we need a threshold voltage to at least a threshold voltage at the gate terminal to induce a channel, right? And whatever the extra voltage is applied will be the effective voltage that is helping accumulating more charges, increasing the depth of the channel, and increasing the conductance of the channel as well, right? So our conductance of the channel is directly proportional to the overdrive voltage. Greater the overdrive voltage, greater will be the conductance of the channel, right? And it determines the electron charge in the channel too. We talked about this, very important, sure. You're going to realize that multiple times in multiple equations, these things will appear again and again. So anyways, just remember that the VOV is this VGS minus VT, or it is this extra voltage beyond the threshold voltage that we apply at the gate terminal, and this plays the effective role. So we apply the VGS to the gate terminal of the MOSFET, but the VT portion of it is just to overcome that barrier, and then this VOV is that extra portion that is helping increase the connectivity of the channel. Okay. So with that, let's move to our next topic. So these are the three parameters again to improve the conductivity of the channel: process transconductance, MOSFET transconductance, process transconductance, the aspect ratio, W over L. The product of both of them is a MOSFET transconductance, and finally the overdrive voltage. Okay, now we will move to the next part of our lecture, and that is the IV characteristics of the MOSFET. Okay. So we saw that, again, going back to the earlier equation. So let me rewrite this equation so it will be helpful. Our drain current is equal to mu n C aux W over L VOV VDS, and GDS is equal to essentially this mu n C aux W over L VOV, right? Okay. Now, from this equations, we saw that, so this drain current equation, we derive this equation when the VDS was small, right? When the VDS value was smaller than the gate to source voltage. And this relation is only valid. In later part of the lecture today, we're going to realize that this equation will change when the VDS will approaches the VGS or even goes beyond VGS or the overdrive voltage, or the effective overdrive voltage that is appearing across the channel. Okay, so the important thing over here is that for this, when the VDS value is small, our channel behaves as a linear resistance, right? And the value of this linear resistance is equal to 1 over GDS. Right, we know that V equals to IR, so R equals to V over I, so V is over here VDS over ID, right, so our VDS over ID is this whole thing, mu n C aux W over L into VDS, so this will be the resistance that you get, right? So our resistance of the channel, or in between drain and the source, which is essentially along the channel, will be 1 over GDS, which will be 1 over mu n C aux W over L, and the overdrive voltage. Now, the most important thing over here that you will realize that as we will decrease the overdrive voltage, the resistance will increase. Now, if I will increase the overdrive voltage, the resistance will decrease. Okay, right? So our resistance is inversely related to the overdrive voltage, or the effective voltage that is appearing across the channel. Okay, now going to the IV characteristics. Okay, so these are the equations that we just derived. Resistance proportional to the conductance. Here's the equation, and over here we just kind of expanded on the VOV equals VDS minus VT. So when the VDS is kept small, the MOSFET behaves as a linear resistance with a value of RDS, whose value is controlled by the gate to source voltage. And again, gate to source voltage is just essentially, right, it is the so you have overdrive voltage is VGS minus VT, so gate to source voltage is VOV plus VT. Since VT is a constant, so VGS is directly proportional to VOV. Okay, so here's the IV characteristics of a MOSFET. On the y-axis we have a drain current, and on the x-axis we have a drain to source voltage. Now look at these characteristics in more detail. So when the VGS is less than the threshold voltage, we know that when the VGS is less than the threshold voltage, no channel will be induced. And if no channel will be induced, it is irrespective of how much voltage we will apply at the drain terminal, nothing will conduct because there are no free electrons in the channel at all to conduct, right? So we have to initially induce a channel. This is what we have been saying so far. Okay, so when VGS is less than the VT, no channel will be induced and no current will flow. Our drain current over here will remain 0 and our resistance RDS will remain infinite. Now as we will increase the overdrive voltage, or as we increase the VGS beyond the threshold voltage, a channel will be induced and the current will flow. Now look over here that our threshold values are the same. So what is happening with the VGS value? Essentially what we are doing is we are increasing the overdrive voltage over here. Okay, so as we increase the overdrive voltage, the current that will flow through the channel from the drain to the source will increase as well, right? And we know that our RDS is inversely proportional to the overdrive voltage. We just said that earlier. Or over here you can also see it. Okay, so as we are increasing now the overdrive voltage, our resistance is being reduced, right? So as we are increasing this overdrive voltage from here to here, so this is also equal to overdrive voltage. As we are increasing the overdrive voltage, the resistance is being reduced, right? And the slope is being increased. So that is why the slope is proportional to, essentially slope is the inverse of the resistance over here, right? So slope is essentially 1 over RDS here. And it depends on the Kn factor. Again, Kn is this entire thing and the overdrive voltage, which is this thing. Okay. All right, so 2 important things going on over here. Actually 3. The first one is when the gate to source voltage is less than the threshold. When the gate to source voltage is less than threshold voltage, nothing will flow because no channel will be induced. Second, as we increase the overdrive voltages, right, the total current that will flow through the channel will increase and the slope will reduce. A slope will increase as well, right, with the slope being 0 over here and the slope being infinity over here, and the resistance will reduce. So as we increase the overdrive voltage, the resistance will reduce. So the resistance over here will be on the y-axis, it will be 0, and on the x-axis the resistance will be infinite. Okay, and the third thing is at a specific overdrive voltage and the gate to source voltage which is greater than the threshold voltage, for example, pick any line over here, for example this one. As we increase in this curve, we have a specific overdrive voltage which is greater than threshold voltage, so the current is flowing. As we increase the value of the VDS, our current is increasing. Okay. So this is what we have talked about. So channel resistance is infinite. We talked about over here. When the VDS is less than VT, I just wrote it over here actually, right? Okay. And it decreases as the VDS is increased above the threshold voltage, right? And we also talked about this, that as you increase the overdrive voltage, the resistance will reduce. As we increase the overdrive voltage, the resistance will reduce. and the current will increase. Okay. All right. So with that, and our resistance or the slope depends on these two factors. One is again these process factors, and the other one is the overdrive voltage. Greater the overdrive voltage, greater will be the slope, smaller will be the resistance of the channel. All right. So with that, let's move to the next slide, which is we are going to very briefly discuss again the enhancement. So if you remember in our first lecture, we talked about the transistor that we have been talking about. I mentioned that it is called as an enhancement MOSFET. It is an enhancement mode MOSFET. There is another one, the depletion mode MOSFET. We will discuss the depletion mode MOSFET towards the end of this chapter. More importantly, now let's very quickly let's discuss again what is again meant by the enhancement mode operation. Quick recap again. So I kind of do this recaps a lot times just to make sure that the key takeaways and the important points of these concepts should be mentioned again and again. So hopefully you guys will remember those. Okay. So quick recap, right? For a channel to be induced, our gate to source voltage needs to be greater than the threshold voltage. Otherwise, no channel will be induced. Second, once that threshold will be achieved, once the gate to source voltage will be greater than the threshold voltage and the channel will be created, once we apply the VDS, the current will flow. And more importantly, again, this VOV is VGS minus VT. Once you will increase this VGS beyond the VT, or more importantly, the greater the overdrive voltage that we will put, the more it will have the conductivity of the channel, right? So we talked about GDS is directly proportional to the overdrive voltage. This is essentially what the enhancement mode operation means, very simply put, right? The greater the gate to source voltage, and in turn, the overdrive voltage. So greater the overdrive voltage, greater will be the conductance of the channel. Or with the increase of the overdrive voltage, the channel conductivity will increase. This is called as an enhancement mode operation or enhancement type MOSFET. We will realize that when we will talk in future about the depletion type, the thing happens opposite. So we will discuss that later part of the course. Okay. So let's talk about our next topic. So by now we have been discussing about when VDS is kept small, right? We derived all of these equations for ID. We derived these three equations. Okay, right? So this is all when the VDS is small. We have a linear resistance. This is the current, drain current. This is the conductance of the channel. Okay. So what will happen when we will increase the VDS value comparable to the gate to source voltage? Okay, where you go? Okay. So what will happen when the VDS is increased? Okay. Another important thing that I have mentioned multiple times previously, when the VDS is small, right over here, when this voltage VDS value is small, the potential that will appear across the channel will remain the same and will remain equal to the gate to source voltage that is applied at the gate terminal, right? So whether the voltage at this end or the potential across the channel at this end, it will remain constant throughout the channel. And this thing will change now when we will apply, because we kind of ignore the VDS. We will see that it will do something different when we will increase the value of the VDS. Okay, so previously we talked about when the VDS was small, the voltage drop across the entire length of the channel was almost constant and equal to VDS. Now let's consider a situation when VDS will be increased. Of course, our first assumption is that we are going to apply a VDS value that is greater than the threshold value, so a channel is induced. So we have a channel here. Okay. So what will happen when we will increase the value of the VDS? Now you can see that the VDS value is variable, and we are going to use this variable VDS to generate a new IV characteristic, or a more realistic or a complete IV characteristics for the MOSFET. Okay. Okay, so what will happen over here is that, right? So once we apply the value of the VGS, and it will induce a channel. Initially, we had a uniform depth of the channel. This was not tapered like that. It was a uniform depth, and the VDS was small because the potential difference that was appearing over here initially at the source end and at the drain end was equal to VGS, right? So this was when VDS was small. When VDS will be large, now we can no longer ignore the VDS value. So what will happen is along the length of the channel now, the potential difference will change from at the source end due to the VDS, the potential at the source end will be 0. And due to this VDS now, and a large VDS, the potential at the drain end will be VDS. So it will increase from 0 to VDS because source is grounded in this case, okay? So at the source end, our potential drop still remains VGS. However, at the drain end, now our potential drop will become VGS minus VDS. Now you will realize that even when VDS was small, this was true. That the potential at the drain end was VGS minus VDS. However, this VDS value was too small that we just kind of ignored it. And we said, okay, this is also VDS, and the potential drop along the length of the channel is exactly the same at all the points along the channel. But now it is, but once the VDS is sufficiently larger, and we're going to talk about what does sufficiently larger mean. This essentially means less than VDS and more than VDS. Slightly less than VDS or more than VDS. We will realize that what will happen. Okay, so what's happening over here? Another important concept that we have talked multiple times earlier is that the conductivity of the channel, the charge accumulation, and the depth, all three of them are directly proportional to the gate to source voltage or the overdrive voltage. Even when the VDS was applied, it is essentially they are proportional to the voltage that are appearing at specific locations of the length of the channel. Initially, our channel was a uniform rectangle because the potential that is appearing at all of these points was exactly same along the length of the channel because VDS was smaller. So that is why it is uniform. However, now we have a much higher voltage that appears at the source end with VDS, and a smaller voltage now appears at the drain end, which is VDS minus VDS. Now, for a smaller voltage, the depth of the channel will be smaller. For a higher voltage, the depth of the channel will be higher. So that is why we have a higher depth here of the channel and a smaller depth here. So what will happen is when we will start to increase the value of the VDS, our channel starts to become tapered. And we are going to discuss a specific case. What will happen when this will become equal? VGS becomes equal to VDS. Then what will happen is essentially our depth of the channel will become 0, effectively. We're going to discuss that situation as well. Okay. Important thing over here is again, since for the effective depth of the channel or for the effective operation of the operation in the induction of the channel, charge accumulation, conductance, all of these parameters are essentially dependent on the overdrive voltage. So you can also essentially call it as the potential that is appearing at the source end is the overdrive voltage, and the potential that is appearing at the drain end is essentially VOV minus VDS. Okay, so this is what we just talked about. So VDS appears as a voltage across the length of the channel, right? From 0 to VDS, 0 at the source end is grounded, and VDS it's appearing at the drain end. Right, so voltage along the length of the channel increases from 0 to VDS along the length of the channel from the source to the drain. So at the source end, we have VGS or VOV because this is just a constant. And then at the drain end now, we have VGS minus VDS, which is essentially this VGS minus VDS. Or effectively, if we ignore the threshold voltage, it is VOV minus VDS. Right, okay, so the channel depth depends on this voltage that is again appearing at different points of the length of the channel, and especially how much it exceeds the value of the VT. So more importantly, it's the overdrive voltage that is appearing at different points of the channel, right? And we just discussed this, that if this voltage is not constant across the length of the channel or along the length of the channel, this means that our depth of the channel will no longer remain constant and it will be a tapered, as we can see in this figure. Okay, now let's move to the next one. So we talked about this. The channel is tapered with the highest depth at the source end, where depth is proportional to the overdrive voltage, and the lowest depth at the drain end, where depth is proportional to the overdrive minus VDS. This is what we just talked about over here, right? That at the source end, our voltage, when the VDS is larger, and we are essentially, more importantly, we are talking about this case, right? This is for the larger VDS case. So, so at the source ends, our the voltage that will appear over here will be overdrive voltage, essentially VGS, but effectively VOV, because the conductance or the induction and all of these phenomena starts to happen beyond VT. And what will at the drain end, it essentially, at the drain end, it's or over here, at the drain end, it will essentially starts to happen at VGS or VOV minus VDS over here. Okay. Now, as we increase the value of the VDS, the channel becomes more tapered and its resistance increases correspondingly. So this thing is important now, right? So earlier we have been saying that when the VDS was small, going back over here, when the VDS was small, our drain current was mu n Cox W over L VOV VDS, and our RDS was 1 over this entire thing. Right, and we have been saying that this thing is this resistance is a linear resistance. However, this is no longer true. As we increase now the VDS, the channel becomes tapered, right? And as we are increasing this VDS more and more, this channel becomes more tapered. So the change in the resistance is no longer a uniform, is no longer a linear model anymore. Okay, so our resistance will increase, right? So as this channel length becomes more and more tapered, so as we are increasing the value of the VDS, the channel length becomes more and more tapered, and this means that the resistance will increase. And as the resistance will increase, the slope will decrease, right? So if I were to, and I'm gonna kind of plot this again in future, shortly, but for example, right? So as the resistance is initially, we had this resistance. So as the resistance will increase, the slope will decrease. So you're gonna see kind of an effect that will not be a linear relationship. Okay, we're gonna discuss that more anyways. Okay, so here are some other figures. Let's look at the figures. So let's look at the bottom figure first. So we have a source end and a drain end. At the source end, our effective voltage that is appearing is the overdrive voltage. At the drain, it is overdrive voltage minus VDS. We have talked about this one multiple times now. Since more voltage is appearing over here at the source as compared to the drain, so therefore the depth is higher at the source as compared to the drain. That is why you can see that this looks like a tapered channel or a trapezium. Okay, now as we will, so as we will increase this value of the VDS, right, this voltage will reduce, right? So this effective voltage will reduce and the channel becomes more and more tapered. We're gonna discuss the case when it will reach to this point. Okay, now let's look at the first we are just discussing a case in which the channel is no longer a uniform or a constant or a regular rectangle channel, but becomes a trapezium or a taper channel. Okay, so let's look at the top figure now. Again, we have a source end where the total effective voltage that is appearing is the VGS, which is VT plus the overdrive voltage. Okay, and then this is the drain end where we have the voltage that is appearing is the drain to source voltage. And this is the kind of effective voltage that is appearing at the drain terminal. We talked about this earlier, that the VGD equals to VGS minus VDS. So that is the voltage that is appearing at the drain terminal. Okay, now because of the VDS, what is the voltage drop along the length of the channel will be, it increases from 0 to the maximum value of VDS. This is what we said over here, right? This thing. Once we apply this VDS, the potential drop because of the VDS along the length of the channel will be 0 at this VDS, right? 0 at the source terminal and maximum VDS at the drain terminal. And we will see that at almost at the middle point of the channel, because of this tapered region, our voltage value will be, our effective voltage will be overdrive voltage minus half of the VDS, right? Or essentially, no. So this is also considering this VGD. Okay. So essentially, the voltage along the length of the channel is half of VDS. If your total voltage drop is 0 to VDS, in the middle, of course, it is going to be half of VDS, right? Okay. So the average voltage that will appear along the length of the channel is going to be half of VDS, and the average voltage that will appear over here at the drain terminal will be overdrive voltage. Essentially, we talked about this, right? So this is overdrive voltage minus VDS. At the middle point of the channel, it will be VV minus half of VDS rather than full VDS. So this is at VDS. Over here, it will be half of VDS. Okay. Now, another thing that you can realize over here is, in this figure is, as you are increasing the value of this VDS, right? As we will increase this value and we will move this line upward, right? We are going to move this line upward in which the VGD effectively reduces. And this is in sync with the tapering, with happening the tapering more. So as the VDS will increase over here, the VDS will increase over here, this line shift upward more, it can reach to this point, where this point is when VGD equals VOV equals VDS. Okay, we're going to discuss in the next slide what will happen to this point. What happened at this point? Okay. So right now we just talked about the taper channel. So the top figure is our VDS is equals to VOT plus VOV. Application of the VDS causes the voltage drop along the length of the channel to vary linearly with an average value of 0.5 VDS, right? So we discussed this point, right? So if along the length of the channel, this is the voltage drop due to VDS, 0 to VDS. So at the middle point, it will be half VDS. And you will realize that as long as the potential at the drain or the grade to drain is greater than the threshold voltage, as long as it is not hitting this point, right? As long as this depth, there is still a depth over here, our channel will still exist at the drain end. We are going to discuss a point when this depth will become 0 later. Okay, and the bottom figure we discuss in detail the channel shape corresponding to the situation in the top figure, while the depth of the channel at the source end is still proportional to the VOV, at the drain end is proportional to VOV minus VDS, right? So this is essentially coming directly from the last thing that we discussed, that at the source end, our potential is VOV, and at the drain end is VGS or VOV minus VDS, ignoring the VT. Okay. So let's look at the IV characteristics again. Initially, we just talked about this IV characteristics in which our VDS was small, our resistance was linear. However, and our channel was uniform depth. However, now we have realized that as we increase the value of the VDS, our channel will no longer remain uniform depth. It will become tapered, and if it will become tapered, this means that this initial linear plot is no longer remain a linear. So another thing that we discussed is as the channel becomes more tapered, right? As channel becomes tapered, resistance increases, right? So if I am following, and we know that the resistance is the slope inverse of the slope of this line, right? Okay, and this is the 0 slope and resistance to be infinite. Okay, so if I am following this line here, okay, so if I have to redraw this curve and I started with a straight line, right? And this is VDS. Now what is happening, and this is ID. What is happening is I started with a very small value of the VDS, very small value of the VDS. The length, the resistance of the channel is uniform, so I am getting a linear line. But as soon as it will sufficiently start to make an impact or start to taper the channel, the resistance starts to increase, right? So the resistance, if the resistance starts to increase, this means that the slope will start to decrease. And so what will happen is it is start going to do this thing, right? So this is the decreasing, the gradual decreasing of a slope or a gradual increasing of the resistance of the channel, right? Okay. So exactly, this is a complete IV characteristics of the MOSFET now. It shows essentially, in the terms of the active operation, it shows two regions, the triode region and the saturation region. Okay, so we have a drain current and the VDS value is applied. Assume over here that of course your VOV is positive, which means that the VGS is greater than the threshold value and the channel is induced. Okay. So what is happening over here? For a smaller values of the VDS, right, the IV characteristics is again linear that we initially discussed in the last slide, right? IV characteristics looks exactly like the same over here. It's a linear characteristics. But as soon as, and over here the depth of the channel is uniform, but as soon as you will reach to this point, the depth of the channel starts to decrease. The depth of the channel starts to decrease. Oh no, there's still depth here. The depth of the channel will start to decrease. The depth of the channel will start to decrease. And we will realize that at this point, okay. And you will realize that at this point, essentially, the depth of the channel at the drain end will become effectively zero. Or we're gonna call it as a pinched off. It will be pinched off, right? So this is exactly what is happening. So as we are increasing the value of the VDS, right, our tapering is increasing, our resistance is increasing, our transconductance is decreasing, right? And similarly, RDS is increasing more, and the GDS is overall decreasing, right? So that is why once we have a linear relationship, this relationship starts to saturate over the time, like this, till a point comes when it will effectively get saturated, or when this will be pinched off, when there is no depth, or when the effective depth at the drain end is zero. At what point it will happen? Again, going back to this figure, you can see that the voltage that is appearing at the source is VOV, at the drain it is VOV minus VDS. So if I will go back here, at the source end it is VOV, at the drain end it is VOV minus VDS. So when VOV, or let's say when VDS becomes equals to VOV, right, the voltage over here will become zero. It's like asking a question on the other line. Okay. Okay, so the voltage at the drain will become 0 volts. So if the voltage at the drain will become 0, this means that there will be no depth to the channel and it will be pinched off. Beyond this point, no matter what, even if you will constantly continue to increase the value of the VDS, there will be no increase in the current. Okay, the current will not stop because we will soon realize that the current will continue to flow and the electrons will still accelerate through the depletion region from the drain end. Even the channel is pinched off there. Okay. So how we can find these characteristics, I guess we just talked in sufficient detail. So charge in the taper channel is proportional to the channel cross-sectional area. We talked about this, right? So this is it, right? So this, as we are moving forward, the tapering is increasing. Another thing over here is the cross-sectional area of the tapered channel is proportional to this. This is essentially the cross-sectional area of a trapezium. You can find it out. And this is proportional to this, right? So this is now the voltage in the triode region, right? So in this smaller region, when the resistance will be linear, right, this is the effective voltage that was appearing. The effective voltage that was appearing on the at every point of the channel was VOV, and this is the effective voltage that is appearing on all the taper channels, which is VOV minus half of VDS. Okay, so we will soon realize that in the drain current equation, we can just replace this by that. Okay, so this was the equation when the VDS was small, right? And this was the voltage that was appearing at the drain end. And we just discussed that what will happen for when the voltage, when this VDS becomes large, the voltage that appears along the length of the channel, the average voltage that appears along the length of the channel is VOV minus half of VDS. VOV minus half of VDS. So what we are going to do is we are just going to replace this value by that. Okay. So we get this. Sorry. Where is it? Sorry. Okay. Okay. Right. So our equation will remain the same. This mu and Cox is again K dash N. So K dash N W over L. VOV is replaced by this VOV minus half of VDS, the voltage appearing across the length of the channel, along the length of the channel, and then the VDS. We're going to call it as equation A. Now this is the equation for this triode region. We have a different equation for this region where it behaves for a small VDS, where it behaves as a linear resistance. We have a different equation for this entire region, for this entire triode region, when the VDS is less than the overdrive voltage and this pinched off is not occurred. The channel is not pinched off. Channel is still tapered or a trapezium. So this is the equation for that. As you can see, for example, if we will reduce this value, if you will start from this equation and if you will reduce the value of the VDS, right? In this equation, if you will reduce the value of the VDS, we can easily neglect this term. We can easily neglect this term and this equation will again become equal to the top equation. Yeah. Okay. We talked about this average voltage along the length of the channel is half of VDS. Okay, so average voltage that gives rise to the channel charge and hence ID is no longer VOV but VOV minus half of VDS. We talked about this, right? So this is the voltage or the average voltage that is appearing along the length of the channel. So another thing that we just did essentially, this is just the repeated information. What we did over here now is we just opened these brackets. So VOV into VDS minus half of VDS square, right? So VOV VDS minus half of VDS square. We can also replace VOV equals VDS minus VT and replace it over here. So we ended up getting another equation like this. So by now we have derived, essentially this is just opening up the brackets, right? This whole thing. By now we had just derived two equations. One equation is for a small VDS, one equation is for a large VDS, and more importantly, triode region. Now let's see very quickly about this pinch off region. We already, I think, discussed most of the details here, but okay. So for the triode region, our description assumes that even when the channel is tapered, it still has a non-zero depth, meaning that, so we know that when we're talking about the drain end or VGD, our voltage that is appearing is VOV minus VDS, right? So for the triode region, we further assume that VDS is less than VOV yet. It has not reached equal to the VOV. So we still talked about this region, right? Okay. And till this region, before this hitting this point, we still have non-zero depth, non-zero depth, non-zero depth, non-zero depth. Exactly at this point, we are going to pinch off. Okay. Okay, so where is figure X? Figure XA. When VGS is, okay, so that is an A. Sorry, going back. Okay, so when we look at the figure X, say VGD is less than the VT, channel won't exist anymore. Yeah, this is essentially the same thing. Coming back to the same plots, that when we will at this, so this is the effective voltage that is appearing at the drain end, right? So this is the VGS minus VDS or VOV minus VDS. So once that will become equal, our this blue line will hit this point, and the effective voltage at the drain will become 0, and the channel will be pinched off, right? So channel won't exist at the drain end. Or in terms of, you can either think it in this term or in the terms of the VDS. When the VDS become equals to the VOV over here, when this VDS becomes equals to the VOV or greater, the channel is pinched off. The channel does not exist at the drain end. Okay, so this is what we talked about. This zero depth of the channel at the drain end is called as the channel pinch off. If we will increase the VDS beyond this value, it will have no effect on the channel shape or size, and the current will be constant. The ID that is flowing through the channel will be constant, and whatever the value that was reached at this point. So this is that point of triode to the saturation region, right? So the current saturates at this value. Okay, and the effective voltage that appears along the length of the channel is now VOV, right? So we can easily replace, and so this is our new equation, and so we can easily replace VDS by VOV square. So using equation Y, right? So in this equation, if you will replace this VDS by VOV, VOV here and VOV here, you can easily, so it will be VOV square minus half of VOV square will be, right? So yeah, if I, okay, ID equals to Kn. Kn again is a multiple of both of these things. VOV minus half of VOV square. I am replacing VDS equals to VOV, add the saturation, so it will be Kn half of VOV square. Okay. Right, so this is Kn MOSFET transconductance parameter, if you remember, then half of VOV square. Okay. And this is, yeah, we just talked about in detail and very briefly, right? So now at the drain end, we have a VOV. At the source end, we have a VOV. At the drain end, our VOV becomes equals to VDS. So that is why it's pinched off, right? And this line also reaches at this point where our gate to drain voltage becomes equal just to the threshold voltage, and our VDS becomes equals to the VOV. And the effective voltage drop along the length of the channel is just half of VOV, and it's no longer in if you remember in the triode region it was VOV minus half of VDS, but since the VDS is now 0, VDS is now VOV, so VOV minus half of VOV equals half of VOV. Okay, so this is the saturation region. The voltage VDS at the saturation region is also denoted as VDS sat. You're gonna see this term appearing in the subsequent lectures in the homework problems as well, right? And we know that at the saturation, our VDS is equals to VOV. Another important point, we discussed that earlier, that channel pinch off does not mean the channel blockage. This does not mean that the current stops flowing, right? The current is still flowing. Look at this plot. The current is still flowing, but the current is saturated. It's constant, right? So what it does is it just accelerates through the depletion region into the drain. Right, it appears as a horizontal line, right? So this is the linear region. This is this triode region when the resistance is decreasing, and this is the saturation region. 3 different ID values. The equation can be rewritten by the overdrive voltage, right? So this is the equation that we derived. Okay, so with this, we are going to finish up our lecture today. In this lecture, we talked about different parameters that increases the conductance of the channel, including process transconductance parameter, aspect ratio, a combination of both MOSFET transconductance and the overdrive voltage. We discussed the IV characteristics of the MOSFET. In particular, when VDS was small, our resistance was linear. Then we discussed very briefly that since we apply more and more overdrive voltage, this increases the channel conductivity. So that is why it is called as an enhancement type MOSFET. Then we discussed what will happen when we further increase the VDS and it can no longer be ignored. At the source end, we have an overdrive voltage or just VDS. And at the drain end, we have VGS minus VDS. And our channel becomes tapered rather than a uniform rectangle. This is that entire discussion on our channel is a taper channel. The average voltage along the length of the channel is half of VDS. The average voltage that will the average voltage across the entire length of the channel that will appear at the drain will be VOV minus half of VDS, this one. We also discussed these characteristics. We have three regions. This is the small VDS region. This is the triode region when it will start to increase and the value is less than the overdrive voltage. And then at the saturation region, which starts to happen at this point, we drive three different equations. We talked about the pinch off, and the pinch off is this: when the channel becomes pinched off, the depth at the channel at the drain end will become zero. The current will continue to start to flow. It will still accelerate, but it will become constant. Okay, so with that, we will wrap it up. Next, in the next lecture, we are going to do a quick example, and we will discuss the PMOS as well. And when we will take it from there, more topics. All right, with that, thank you so much and have a good day. Bye bye.